Alaikum, sir.
Islam.
Sir, I have a few doubts.
Yes, you have doubts.
Uh,
In which question?
Sir, in all the three questions, I have to ask something. First question, I don't know. Second and third, I have to ask something.
Second.
Sir,
First you did no. You tried first question?
I tried first one, but I'm not
Okay.
getting it exactly.
So the first question says you have a glass sphere of radius 2 centimeter. So this is a glass sphere. The radius of the glass sphere is 2 centimeter. A small air bubble in a glass sphere of radius appears to be 1 centimeter from the surface when looked at along a diameter. So this is the diameter. So someone is watching this glass sphere from here. This is the center. And this small air bubble, this is the small air bubble. This appears at 1 centimeter from the surface. So air bubble appears at this point. That will mean that this is the image. This is the image of air bubble. This is the image of air bubble. Image of air bubble is this. And this is the surface from which refraction happens. So you have image distance. This is glass sphere, its refractive index is 1.5.
Sir, how image distance is 2 centimeter?
Sorry,
Sir, how image distance is 2 centimeter?
image distance is not 2 centimeter. Image distance is 1 centimeter. It's saying small air bubble in a glass sphere of radius 2 centimeter appears to be 1 centimeter from the surface. So bubble is somewhere inside the surface which is not given. Maybe bubble may be here. This will be the object. It's not given at what distance this bubble is. But the thing which is given is the image is at 1 centimeter from the surface.
So we need to find U.
You're supposed to find this.
Okay.
So what you can do is you have N1, which is rarer medium 1. You have N2, which is refractive index of denser medium, which is 1.5. Object distance is not given. You have image distance, which is minus 1 centimeter. The radius of curvature is minus 2 centimeter. Refraction is from denser to rarer.
Sir,
Yes.
sir, how V and R are minus? That one I didn't get it.
Okay. This is your object. So ray must be going in this direction, right? This is the direction of ray and this is the pole. So when you measure the distances, you go from pole to image. Then you go from pole to object. You're moving in the direction opposite to that.
Okay. Okay, sir.
So N1 by minus U, not N1, N2 by minus U plus N1 by U, V is N1 minus N2 divided by R. Just substitute all values here. Your N2 is 1.5 divided by minus U plus N1, which is 1, V, which is minus 1, N1 minus N2, 1 minus 1.5 by R, which is minus 2. Is it clear now? Can you get the value of U?
Yes, sir, it's clear.
See the next question, question number 2. Just note it down, then we'll do the second question. Does anyone else try this assignment? It's okay. So I'm solving each and every question. Huh? This was first question. Question number 1. Just tell me once you have written. Don't solve the second question.
Yes, sir. Done.
What about the rest, Sania, Nazira? All these questions were for are already in previous year's questions of CBSE. See, the second question says an empty spherical flask of diameter 15 centimeter is placed in water of refractive index 4/3. So you have water. And in water, you place a flask, sealed flask. Means inside the flask, what you have, air or water? It's a sealed flask.
Yeah.
Air. So inside the flask, you have air. And outside, you have water. Now he's asking, a parallel beam of light strikes the flask. Where does it get focused? So you take a parallel beam. It strikes the flask. You have to decide where it will focus. The radius of curvature of the flask is 15 centimeter is the diameter. Diameter of the flask is 15 centimeter. So the radius of the flask is 7.5 centimeter is the radius of the flask. So what we can do is, this is the refraction over the surface. Rays are coming from water to air. So refraction is from, in this question also, that is denser to rarer. So water is denser, so its refractive index is 4/3 given. Air is rarer, it's 1. Object is at infinity, so object distance is infinite. Your image is at 7.5 centimeter, image distance is 7.5 centimeter, it's positive. See, this is the pole. You are going in the direction of light. No, image distance is not 7.5 centimeter. Image distance is what we have to calculate. The radius of curvature, you're going in the direction of light, it's plus 7.5 centimeter. Apply the relation N2 by minus U plus N1 by V is N1 minus N2 divided by R. So substitute all values here. N2 is 4/3. U is infinite, so it will be 0. N1 is 1. V is unknown. N1 is 1. N2 is 4/3. And radius of curvature is 7.5. So it's 0. 1 by infinity is 0. Plus 1 by V is, it's 1 minus 4/3, it's minus 1/3 into 7.5. So you can take reciprocal on both the sides. We'll get V is minus 3 into 7.5 centimeter. So that is the second part to it.
Oh,
Yes.
so if parallel beam of lights are coming, that means the object distance is infinity.
Yeah. Object distance is infinity.
Okay. Okay.
Just one last question. After that, we will start lenses.
Done.
Okay. Okay, next, third question. A sunshine recorder globe of 30 centimeter diameter is made of glass of refractive index 1.5. A ray enters the globe parallel to the expanded position from the center of the sphere with a ray crosses the axis. So it's a globe, sphere again. Its diameter is 30 centimeters, so radius of curvature is 15 centimeter. Parallel rays incident over it. So rays are coming from infinity, they incident over this. The refractive index is 1.5. N2 is 1.5. Surrounding medium is air, N1 is 1. Find the position from the center of the sphere where the ray crosses the axis. So you need the image distance. So for the first surface, this is pole. N1 is 1, N2 is this, object distance is infinity. You need to find the image distance. Rays are coming from air to glass. So this is refraction from rarer to denser. Rarer to denser medium. So for rarer to denser, this is the relation N1 by minus U plus N2 by V, which is N2 minus N1 divided by R. So substitute all values here. How much is N1? N1 is 1, U is infinity. N2 is 1.5, V is unknown. N2 is 1.5 minus 1 by radius of curvature, which is 15. See, when you go in the direction of light, it's plus 15. So we have 1.5 by V is 1.5 minus V is 0.5 by 15. So get the value of V. Just cross multiply it. It's 1.5 multiplied by 15 divided by 0. So it's 3. You get V is 45 centimeter. So that's the image distance, 45 centimeter. From the surface, the image will be at 45 centimeter. But see, 45 centimeter is outside the sphere. Here, this is the image. But it's not possible because if you converge the rays at 45 centimeter from this point, then it will again refract over the surface. So you have to consider second refraction also here. Here, you should consider second refraction. So for first surface, this is the object at infinity. And this is the image. You will use this concept in the next derivation also. This is image for first surface. Image for first surface. This is the image for first surface. But for the second surface, if I take the second surface, this second surface, for the second surface, this image will act like an object. This image here will act like an object for the second surface. So for the second surface, it's 45, this is 30, and this is 15 centimeters. So let's take refraction for the second surface. For the second surface, this is the object. This is the object for the second surface. So for the second surface, your object distance is 15 centimeter. This is pole. For object, you are going in the direction of light. So it's plus 15 centimeter. The next is image distance is unknown. The radius of curvature. For radius of curvature, you will move from P to C. You will move in the direction of opposite to that of light. So it's minus 15 centimeter. N1 and N2 are same. N1 is 1, N2 is 1.5.
Sir, P to
Yes.
C moving in the direction of air, right?
P to C, no? See, light is going to the right and you are moving from P to C. Opposite to that.
Sir, the second refraction light will go left, right?
No, light won't go left. Light is going to the right hand side direction. It gets refracted over this point.
Okay.
This is the virtual object. So you will write N. No, now the refraction is rays going from denser to rarer. So this is refraction from denser to rarer. It's N2 over minus U plus N1 over V is N1 minus N2 by R. Let's substitute all values here. So how much is N2? N2 is 1.5 by minus U minus 15. N1 is 1. V. N1 minus N2, 1 minus 1.5 by R, which is minus 15. So you can write this is minus of 0.5 by 15. So we have 1.5 by minus 15 plus 1 by V is minus of 0.5 by 15. I think you can calculate the value of V. Do it. So this was your assignment question. Only the third one was tough. Amir, is it your batch? Amir Abid? Or you have joined from some different name?
There is Noor.
Okay, that's Noor. Noor, change your name.
Sir, for second refraction, I is acting as the object, right?
Yeah, I is the object for the second surface.
So we'll move from rarer to denser, right? Like
See, Abdullah. Ray is going from denser to rarer only. At this point, your ray will suffer second diffraction.
at that point only.
Yes.
Yes, I got.
It's a virtual object.
But if the after the first refraction, if the image was forming in the glass sphere only,
Then there's no need to for second diffraction.
then okay.
Like in all previous questions, in question number 1 and 2, you were getting the image inside the glass only. So there was no need of second diffraction. Okay, so this completes your spherical refracting surface. Now let's move on to lens. See, now a lens consists of two spherical refracting surfaces. If you connect two surfaces, then you get lens. If you have various types of lens, we have three types of surfaces. One is convex spherical surface, another is concave surface, and another surface is plane surface. These are the three types of surfaces we have: convex, concave, and plane. So you we make a lens by combining any two type of surfaces. Means you can combine two convex surfaces, two concave surfaces, one convex, one plane, one convex, one concave. So we'll get different types of lenses. So if both the surfaces are convex surfaces, you will get double convex lens, or we call it as biconvex also. If both the surfaces are concave, then we get double concave lens or biconcave also. If one is plane, another is convex, then we call it as plano-convex lens. One is plane, another is concave, we call it as plano-concave. This is plano-convex, this is plano-concave. If one is convex, another is concave, we call it as convexo-concave. If one is concave, another is convex, we call it as concavo-convex. So these are the types of lenses we have. The 6 types of lenses we have. Write it. Fatma, any doubt in lenses?
No, sir.
This lens is even important in spherical refracting surface. Written?
Yes.
Okay, from now onwards, whatever we'll do for a thin lens. All theories we will do for thin lens. So thin lens means a lens whose thickness is very, very small. This thickness is negligible. This thickness is so small that this end1 and end2 are very, very close. There is no difference between end1 and end2. Thin lens. Now let's define optical center of a thin lens. If you incident a ray on a thin lens, then the ray passing through its optical center will go without any refraction. It will not deviate, it will go straight if it is passing through the optical center of the thin lens. This is valid for both the type of lenses, for concave as well as the convex lens. Even if you have a concave lens, ray will pass through the optical center without any refraction. Ray will pass through the optical center without any refraction. It will go straight. Thin lens. The next is focus and focal length. So I should draw it. Should draw it again. See, what is focus and what is focal length of a lens? A lens have two types of focus, first principal focus and second principal focus. Now let's see what is the difference between first principal focus and the second principal focus. See, focus of lens. So first principal focus. First principal focus. So if rays are coming from first principal focus or they are converging at first principal focus for the concave lens, then after refraction, they will become parallel to principal axis. So rays passing through, we use this statement for a convex lens, or converging at we use this statement for a concave lens. First principal focus, first principal focus becomes parallel to principal axis, becomes parallel to principal axis after refraction. So after refraction, ray will become parallel to principal axis. That's the first principle. Sorry, that's the first principal axis. Principal focus. So this, yes.
That is rays passing through convex.
Yes, I'm coming to it. If you have a convex lens, and I call this point as the first principal focus, then if rays are passing through it, the first principal focus, then after refraction, these rays will become parallel to principal axis. So when I say passing through, that means this statement is for a convex lens. This statement is for a convex lens. When I'm saying it's converging at, means this statement is for a concave lens. So if you have a concave lens, if you have a concave lens, is a concave lens, and rays are coming parallel to principal axis, after refraction, rays will diverge. After refraction, ray will diverge. When you produce them in the backward direction, then they appear to meet at a point. Sorry. So incident rays at a point, and that point is known as the focus. This is the first principal focus. After refraction, these rays will become parallel to principal axis. This is first principle focus. So if you take converging rays, you converge those rays at a point which is first principle focus, then after refraction, ray will become parallel to principal axis. For a convex lens, is a real point. If rays are coming out of it or rays are passing through this first principle focus, then after refraction through the lens, they will become parallel to principal axis. That's first principle focus. This is the first principle focal length. This is optical center. The separation between the optical center and the focus is known as focal length. So we call this as first focal length. This as the first focal length. This is the first focal length. We will do sign convention for lens. For lens, we measure all distances from the optical center. Like in spherical refracting surface, we were making all distances, we were measuring all distances from the pole. Here we measure all distances from optical center, not from pole. So we'll tell. Fatma will tell. Fatma, this F1 will be positive or negative? Measured
Positive.
positive.
In first one,
F1, this one.
this will be positive.
This will be positive. Nazira, what do you think? This will be positive? Fatma is correct?
I think it's negative.
It's negative. Fatma, Nazira is correct. It's negative. See, you will start from O and you will go to F1. You're going in a direction opposite to that of the light. Light is going to the right hand side. You start from O and you go up to F1. You're moving in a direction opposite to that of light. So it will be negative. Okay, Fatma, try here. This is optical center. And measure this one, this F1 for the concave lens. What do you think now?
That is positive.
That is positive. You're going from O to F1. You're going in the direction of light. So this is positive. But first principle focus is not very useful. We don't use this quantity in numericals or in derivation. Whenever I say focus of a lens, that doesn't mean first principle focus. When we say focus, we mean second principle focus. When we say focal length of a lens, we say second principle focal of the lens, not the first principle focus of first principle focal length. First principle focus, this is second principle focus. Second principle focus. So second principle focus means this is the lens. So this is the lens. Second principle focus means point at which parallel rays converge. So if you take a convex lens, the parallel rays will converge at a point. This is your second principle focus, F2. This is the optical center. This is the second focal length. Similarly, if you take a concave lens, you incident parallel rays over it, it will diverge the rays. When you produce it in the backward direction, they appear to meet at a point. We call this point as the second focus of the concave lens. And the separation is focal length. So second principle focus, point at which parallel rays converge or appear to converge. So they converge for a convex lens and they appear to converge for a concave Sanya, just check whether this F2 is positive or negative. What sign convention you will use for it? No. See, start from optical center and go up to F2. Starting point should always be optical center. When you start from O and you're going to F2, you're going in the direction of light, it's positive. And for concave, it's negative. So by default, focus is second focus. So whenever we talk about focal length of a lens, that means second principal focal length. Whenever we talk about the focus of a lens, that's the second principal focus. It's always second principal focus, never first principal focus, unless it is mentioned. If he asks you to calculate first principal focus, then it's a different thing. If he asks you to calculate the first principal focal length, it's a different thing. But if it is given in the question that calculate focal length, that means second principal focus. Do it. Can I scroll it?
Yes, sir.
Do it. Can I scroll it further? Written. Second principal focus is over. Sorry. After second principal focus, this is something very, very important. Lens maker formula. See, this lens maker formula is a 5. This lens maker formula along with the formula of spherical refracting surface is a 5-marker question. If you look at last 10 years papers of CBSE, you will find in almost 4 years they gave this question. These two derivations together, spherical refracting surface that we did in the last class and this one. The one for lens maker formula. See, this is lens maker. So see, what is lens maker formula exactly? Lens maker formula is a relation between, it's a relation between focal length of lens, focal length of lens. So when I'm saying focal length, that means which focal length? First focal length, second focal length, which one? Yes, which focal length?
Second.
Second. By default, it's always second. Focal length of lens, the radii of curvature of the lens, radii of curvature, and refractive indices. Refractive indices of lens and surrounding. This is lens maker formula. It's a relation between the focal length of the lens, the radii of curvature of both the surfaces, and refractive indices of lens and surrounding. That's lens maker formula. So it's a convex lens. Double convex lens. This is the optical center of the lens. It's a thick lens. But just for the sake of derivation, I'm drawing a very thick lens, but we will do all calculations under thin lens approximations. This is the first surface, X, P1, Y. This is the second surface, X, P2Y. This is your object, O1. So what you can do is, from this object, you can incident a light ray here. This is your light ray, incident light ray. This is the center of curvature C1. This is the center of curvature C1. And yes, see, this ray is moving from rarer to denser medium. So this is the normal. So when it moves from rarer to denser medium, the ray will bend towards the normal. So this ray will bend towards the normal. It should go straight in this way. And that should be the final image. It should go straight. But what do you think? Can this ray travel in a straight line, or it will undergo a second refraction? Yes, what do you think?
It will undergo second refraction.
Second refraction. See, this is the false surface. Let's say this is medium of refractive index N1. This is the medium of lens N2. The ray is going from N1 to N2. Now this ray is going from N2 to N1 again. So there is another refraction. So here there's another refraction. So for you need a normal here. So for this surface xp to y, this is the center of curvature. Now let's drop another normal. For the second surface, this is the normal for the second surface. This is the normal for the second surface. This is normal for the second surface. Now your ray is going from N2 to N1. N2 is a denser medium, N1 is a rarer medium. So this ray will bend away from the norm. So see, this is the direction of ray if it does not refract. If you don't have second refraction, then ray would have gone in this direction. Ray would have moved in this direction if there is no second medium, there is no second refraction. But see, the ray, this ray will again gets refracted. And this time it's moving from denser to rarer. So this is the original direction of the ray. This is the normal. This ray will bend away from the normal. So it will bend in this way. This will bend away from the normal. Away from the normal. So this will be your final image. So this is your object. And this will be your final image. This, you can say that this is some intermediate image. So we have two refractions. Say for the first surface xp1y, this O1 is the object. This is the object for first surface. This I1 is the image for first surface. This is the image for first surface. And this image will act as an object. This is this I1. This I1 is object for second surface. And this is the image of second surface. So this is the entire refraction. So let's summarize it. This is convex lens. The first surface xp1y, your ray is moving from rarer to denser, it will bend towards the norm. If there is no second diffraction, then this ray will go straight or meet over here. So for the first surface, this is object and this is image. But there is another refraction. So this ray will again refract. This time it's going from denser to rarer. It will bend away from the normal and meet here. So yeah. It will meet here. So for the second surface, this I1 is the object and this I is the image for the second surface. This is it. Draw this ray diagram, then we will do the calculations. Yes, Fatma, blue and red lines are the normal. This red is the normal on the second surface. This blue is the normal on the first surface. This is normal for x p2y and blue is normal for x p1y for the first surface. Okay. Everyone have drawn this diagram?
No, sir, just a second. Okay, sir.
Okay. So everyone have written. Huh? Okay. Now we have to derive lens maker formula, the relation between the focal length, the radius of curvature. So let's first point out which is object distance, which is image distance. We will take all distances from the optical center. P1, O, and P2 are very, very close. So I'm writing thin lens approximation. P1, O, and P2 are very close. All 3 points are very, very close. P1, O, and P2 are very, very close. So see here. This is the object distance from O1 to O is the object distance U. This is the image distance for the first surface. I call it as V1. And this I is the final image distance. This is V. From O to C1 is the radius of curvature of the first surface. Then O to C2 is the radius of curvature of the second surface. Mark these distances in your ray diagram. R1, R2, UV, and V1. What topic are you doing in school?
Sun.
Which one?
Diffraction. Wave optics, diffraction.
Wave optics. Refraction. So interference is over.
Yes, sir. Today only we finished interference.
Hmm?
Today only we finished interference.
Sure. Because interference is very time consuming thing. For interference, I will need like some part of wave mechanics that you did in class 11th. Interference is lengthy. Noted?
Yes.
Okay, let's start the derivation. I will rub it. See, just look at your ray diagram and decide whether the first refraction at the first surface is from rarer to denser or denser to rarer for the first surface. Derivation is very easy. If you know the spherical refracting surface, then it's 3-4 line calculation. Yes.
Real to denser.
Yes, the first one is for refraction from rarer to denser. So for this first surface, the refraction is from rarer to denser. We can just write this as first surface. First, what's the name of the first surface? XP1Y. So first surface XP1Y. Refraction is from rarer to denser medium. So if refraction is from rarer to denser, then we can use this relation N1 by minus U plus N2 by V. See, what is the image distance for second surface? Is it V or V1? First surface.
V1.
Yes,
V.
not V. So see, for the first surface, this is the image now.
Okay.
So this is V1. So it's N2 by V1, which is equal to N2 minus N1 divided by R. That's first equation. For second surface, for surface X P to Y. See, for second surface, rays are moving from denser to rarer. So the refraction is from denser to rarer medium. Refraction is from denser to rarer. Denser to rarer. So if refraction is from rarer to denser, then you can write the equation as it's N2 y minus. What is the object for the second surface? Look at the ray diagram. What is the object for the second surface?
V1.
For xp to y, this I1 is the object for the second surface. This is image for first surface and object for second surface. For second surface, your object distance is V1. So it's N2 by minus of V1 plus N1 by, what is the image distance for the second surface?
V.
It's V. This is image for the second surface, V. So N1 by V is N1 minus N2 over R2. Just add 1 and 2. So when you add equation number 1 and equation number 2, what we get is, we get N1 by minus U plus N2 by V1 is N2 minus N1 by R1 I'm adding this equation. So it's N2 by minus V1 plus N1 by V is N2 minus N1 by R1 plus N1 minus N2 by R. See, N2 by V1 and N2 by minus V1 will cancel out. First cancellation. You can take N1 common here. So when you take N1 as common, you are left with minus 1 by U plus 1 by V. So in both the equations, you can take minus sign common here. So it's N2 minus N1 by R1. Take minus sign common here. We'll take minus sign common. This will be N2 minus N1 by R2. So what we can do is we can write this as N1. This is simply 1 by V minus 1 by U. See, in both the equations, you can take N2 minus N1 as common. And this is 1 by R1 minus 1 by R2. This 1 by V minus 1 by U can be written as 1 by F. Which focal length is this? First focal length, second focal length?
Second focal length.
It's always second focal length. Huh? So we can make these substitutions. You will get N1 by F is equal to, it's N2 minus N1, 1 by R1 minus 1 by R2. I need F. So what we can do is we can keep this F here and divide this equation by N1. So it's N2 by N1 minus N1 by N1, 1 by R1 minus 1 by R. See, N2 by N1 can be written as N21 minus 1, 1 by R1, 1 by R2. So N21 is refractive index of medium 2 with respect to medium 1. So this is refractive index of medium 2 with respect to medium 1. That's N21. So it's N21 minus 1, 1 by R1 minus 1 by R2. This is the lens maker formula. This is valid for all types of lenses. When you use this relation in numerical, we have to use sign convention. This is focal length, second focal length. This N21 is refractive index of medium 2 with respect to 1. Medium 2 is medium of lens. You can say this is a refractive index of medium of lens with respect to surrounding. Now, from this equation, you can decide whether a given lens is converging or diverging. If your focal length comes out to be positive, then your lens is converging. If focal length is negative, then the lens is diverging. So, and always remember, N1 is always refractive index of surrounding. N2 is always refractive index of the lens. Do it. Then we'll do numericals on this.
Sir, N1 is refractive index of
Surrounding medium. And N2 is the refractive index of the medium of lens. Tell me if you have doubts in any step. See, this derivation is super important. Yes, written. Written? Yes, everyone had written up to here? Let's do one formula based numerical. This will just clear how to use this lens maker formula. So you have a double convex lens is given. This is the optical center. The radius of curvature of this face is 10 centimeter. The radius of curvature of this face is 20 centimeter. Refractive index of the surrounding is 1, N1 is 1. Refractive index of the medium of lens is 1.5. Calculate its focal length. Calculate focal length. So when you calculate focal length, first of all, mark your C1 and C2. These are C1 and C2 are important to decide the direction or sign of R1 and R2. This is P1, then there should be C1. This is P2, there should be C2. See how to decide where is C1 and C2. This is the first surface. This will complete sphere in this direction, right? So C1 should be here. This is second surface. If you look at the curvature, it will complete sphere to the left hand side. That's why C2 should be at the left hand side. So once you have C1 and C2, just mark the radius of curvature, that's R1, and mark this radius of curvature also, this is R2. So light is coming from here. That's why I'm calling this as P1. First surface is the surface at which light strikes first. That's the first surface. And this is the second surface. So for the first surface, your N1 is 1, N2 is 1.5. Now Sania will tell. Sania, this R1 will be positive or negative? Just go from O to C1. It will be positive or negative? See, you start from O and go to C. This will be positive. Plus 20. Good. Fatma, what about R2? It will be positive or negative. Start from O and go to C2.
Negative.
It will be negative. So it's minus of 10 centimeter. So N1 is 1, N2 is 1.5, R1 is 20, R2 is minus 10. U is, I need focal length. 1 by F is, it's N2 1 minus 1. 1 by R1 minus 1 by R2. So this N2 1 you can write as N2 by N1 minus 1. 1 by R1 minus 1. Substitute all values with proper sign and get the value of F focal length. Do it. Substitute all values. You have R1, R2 with proper sign. Substitute the values of R1 and R2 and get the value of focal length. Okay, Abdullah. We'll check. What about the rest? Noor? Your answer? What about the rest answers? Fatma, Nazira, Dur. Seems no one is doing calculations. See, 1 by f is n2, which is 1.5, by n1, which is 1 minus 1, 1 by r1, which is 1 by 20, 1 by r2, which is minus 10. So 1 by f is, it's 0.5 into 20 is LCM, it's 1 plus 2. So 1 by f is 0.5 into 3 by 20. So we get f to be equal to 40 by 3 centimeter. Abdullah, it's not 33.3, it's 13.3. Is it clear?
Yes, sir.
Okay, so that was about, no, Fatma, it's 40 by 3. 40 by 3 is the answer. So it's coming out to be positive. That means the given length is conversion. It's coming out to be positive. I didn't get you, Fatma. What is 30 by 20? LCM you're saying?
Yeah, sir, the LCM.
No. See, this is 20 and 10. The LCM will be 20. When you divide 20 by 20, you get
The upside will be 30, right?
no.
Three
See, you divide 50 by 20, you get 1. You multiply that 1 with 1, so it's 1. 10, you divide it by 20, you get 2. Then you multiply it with 1, you will get 2. It's not 30 by 20, it's 3 by 2. That's right. It's LCM. And if you want to do cross multiplication, Fatma, then it will be 200 in the denominator. It's another way, just multiply them. It's 200. 10 plus 20. It's 30 by 200 if you want to cross multiply.
Okay, sir, I got a mistake.
Okay, so this is over. Lens maker formula. In the next class, we'll do few numericals and we start the lens formula, the combination of lens and boosters. I'm sharing a small assignment. Having this time, the assignment will have 4 to 5 questions on this only lens maker formula. Okay, so let's stop here. Continue this in the next class. Love is.
Love
Thank
sir.
you.
Love is.